In this lab, students analyzed the motion of a spring system that was oscillating and compared it to a computer model of the spring system. When the motion of the two systems were graphed, students found that the two models followed similar motion patterns. There were three main physics principles used in the lab. The first was Newton's second law, which states that the final velocity of the spring can be found using initial velocity, net force, mass, and delta t. Furthermore, it states that the final position can be found using initial position, velocity, and delta t. The next was Hooke's law, which states that force can be found by multiplying the spring constant by the stretch. The next was the energy principle, which states that the total change in energy is the sum of all changes of energy. Furthermore, it states that, if there is no work done on the system, the total change in energy will be zero. First, students analyzed the motion of a spring system using tracker. Students found that the mass of the object was 0.402 kilograms, the stretch length was 0.7 meters, the initial position was negative 9.022 e to the negative 2, negative 0.638, and the initial velocity was 0. Students then calculated spring stiffness using the equation K is equal to 4 pi squared times mass over 1 period squared. Once the values were plugged in, the spring stiffness was found to be 7.17 newtons over meters. Next, the relaxed length was found using the equation L sub 0 is equal to L minus mg over K. Once the values were plugged in, the relaxed length was found to be 0.1506 meters. After students created the tracker model, they created a model using GlowScript. First, students plugged in the mass of the object and the initial position and velocity found in tracker. Students also read in the CSV file of the data from tracker in order to compare the two models. Next, students plugged in the values for K and L sub 0 that were solved for using tracker data. Students also defined L, L hat, and S using their physics definitions. Students then plugged in the equations for kinetic energy, gravitational potential energy, and spring potential energy. Next, students used a calculation loop to predict the motion of the spring. After the initial energies were defined, the forces were found. The force of gravity was defined as negative g times the mass, and the spring force was defined as L hat times S times negative k. Next, net force was found to be the sum of these two forces. Finally, Newton's second law was used to predict the new velocity and position of the ball. Next, the changes in energies were found by defining the energies, then subtracting the current energy from the initial energy. Finally, using the energy principle, students found total energy to be the sum of all energies, and the change in energy to be 0. Unfortunately, due to an unsolved error in the GlowScript code, I was not able to get a reasonable graph. However, this is an example of what the graph of the computer and real-life model should have looked like. As you can see, the blue represents the real-life model and the red represents the computer model. While both models follow similar motion patterns, the real-life model has less range of motion, most likely due to air drag, which was not factored into the computer model. Again, due to the unsolved GlowScript error, I was unable to get a reasonable energy graph. However, this is an example of what it should have looked like. As you can see, this graph satisfies the energy principle, since at any point, when all changes of energy are added together, they equal to 0. Thus, the total change in energy is 0, satisfying the energy principle. In the lab, a period t was found by finding the time it took to complete 3 oscillations using the x position data from tracker, then dividing by 3 to find the average. This average was found to be 1.48776 seconds. Once t was found, it was used to solve for k, as seen. When the y position data from tracker is used, t is found to be 1.51933 seconds. This is fairly good data, since the periods from the x and y position data are supposed to be identical, and these numbers are very close together. The reason for the differences is most likely due to human error when selecting points for a tracker to use. In conclusion, this lab used Hooke's law, the energy principle, and Newton's second law to compare a real-life model and a computer simulation of a spring moving. In the future, one way to make these two models more similar is to factor in air drag in the computer model. This lab also explored the different energies of the system and found that total change in energy is 0 when no work is applied. Finally, students explored the similarities of time periods when using the x and y position data.